Okay, welcome back, everybody. Okay, so last time I ended with a discussion of one of Euler's most famous contributions to math, which is the equation e to the I pi plus 1 is equal to 0. So I included a derivation of this identity where it came from, so kind of the most straightforward way of seeing this without me talking about a lot of complex analysis or just basic arithmetic of complex numbers and what's called polar form of a complex number is thinking about this in terms of those power series. Okay, so if I look at the power series for e to the x, the Maclaurin series even, for e to the x, and just plug in I times pi, or well, that will do it too, but I times x, you can actually see sine and cosine showing up there, and that's why this plugging in pi here is special, right? So the actual the actual thing here that this relied on was this, what I proved last time was this identity, e to the ix is cosine x plus I times sine x. Okay, so this is the thing that does it. If you plug in pi here, you get minus 1. So e to the I pi is equal to minus 1, or e to the I pi plus 1 is equal to 0. So this is frequently called Euler's formula. And is cited very often as kind of like, the pinnacle of mathematical beauty in terms of how simple it is, and it relates these 5 like fundamental constants in math in one equation like this. Okay, so this is definitely not the only thing we can pick out from Euler. As I said, he's arguably the most prolific mathematician of all time, so there's a lot of stuff to talk about. Another example of something to talk about that Euler did is called the Basal problem. So Euler solved what is called the Basal problem. And so Basel referring to the city. So the Basal problem was called the Basal problem, I believe, because it was originally posed in 1650 by an Italian mathematician, but I think it was associated with the town of Basel because of the Bernoullis originally. So Euler was also, I think Basel was also Euler's hometown. So I'm not actually sure if if the Basel problem was called that because that's Euler's hometown or because it was earlier worked on by the Bernoullis. I actually want to say that it's because it was earlier worked on by the Bernoullis, but I could be wrong. So that's a mystery. I'll have to look that up later. But yes, this references the city in Switzerland. So what is the Basel problem? So the Basel problem is the following: compute the sum that is 1 plus, so this is 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 plus 1/36, and so on, right? With the pattern here being, of course, this is like 1 plus 1/2 squared plus 1/3 squared plus 1/4 squared plus 1/5 squared, and so on, plus 1/6 squared. Keep going. Rewriting this in sum notation, this is the sum from n equals 1 to infinity of 1/n squared. Okay, here's the sum that is going to be computed. Now, one of you asked last time, what does it mean to compute one of these infinite sums? Okay, so that's a good question, right? Compute the sum implies that I can actually do all of this addition. Well, I can, right? But I have to be careful. Okay, and so again, this is something that, to be fully careful, was not even something that Euler did when he solved the Basel problem. So his argument here had some, it wasn't entirely rigorous. The argument is amazing. It's actually one of the slickest, coolest arguments I've ever seen in a proof. And I might go into it when we get on to the next bit. After I finish this block and we get into the freeform stuff, because the results of the poll are in. It's equally split among all of the options I gave, basically. So that means that I'm just going to try to pick the most accessible things from those three topics. So anyway, when I'm talking about analysis, I may actually talk about the Basel problem a bit because it's going to tie into some other things. Some of that I'm going to mention right now. So what does it mean to compute this sum? Okay. Well, before we can talk about that, I'm going to give some examples. So remember that Leibniz was asked by Huygens to compute a particular sum. So recall Leibniz had previously, and Leibniz wasn't the only one to figure out how to do this, but Leibniz had previously computed the sum which was given to him as a challenge by Huygens. Let me look up the actual particular sum. Oh, here it is. So it was, I went over this before, so this is like the sum from n equals 1 to infinity of a 2 over n times n plus 1. And the way that he did this is Leibniz noticed that you could split this fraction, right, into partial fractions. So this is the sum from n equals 1 to infinity of, the way that he split this was, he wrote this as 2 times 1 over n, not 1 over 2, 1 over n, that's an n there, 1 over n minus 1 over n plus 1. Okay, and so when you wrote it out like this, what you ended up getting was 2 times, you had this, if you just wrote it out, you had 1 minus 1/2 plus 1/2, right, minus 1/3 plus 1/3 minus 1/4 plus 1/4, and so on. And of course what happened is these things canceled, Now, Leibniz did this rearrangement non-rigorously, and so these cancel all the way out. These infinitely many terms all cancel, and you're left with 1 plus 0 here if you like. And so Leibniz said that this was 2. Okay, and this is an example of a telescoping series. And I explained before that a telescoping series was a sum like this that telescoped. Okay, it collapsed, it folded on its ends. Okay, now, as I said, this wasn't a rigorous way of doing this. So what is the rigorous way? Well, if you have a sum like this is called a mathematical series. Okay, so a series is just a sum of some terms. So I have a starting point, n is equal to, I'll call it n is equal to, say, j is my starting point. I have an ending point, but let's say it's an infinite series, right? So my infinite series is a sum from some starting point, and there's infinitely many sums, so I'm summing from the jth term to infinity. And my terms in my series are made up of what is called a sequence. Now, a sequence is just a collection of numbers. Okay, so I'm going to denote my sequence by a sub n. So if I write out this series, this is just the sum. I start at the jth term, so that's a sub j. And then the next would be a sub j plus 1 plus a sub j plus 2 plus a sub j plus 3. These are just indices. Okay, these are just telling you how to index, or which thing you're picking in the sequence, whereas your sequence a sub n is just a collection, right? So n equals 1 to infinity. This is just literally a set of numbers. A sub 1, a sub 2, a sub 3, a sub 4, and so on. Now, infinitely many of these could be 0, for instance, right? So if all of these are 0 after a certain point, right? So say all of these are 0 after like a sub 3, right? Then this series that sums all of these entries in the sequence up to, or all the way to infinity, starting at 1, would really just be the sum a1 plus a2 plus a3. Okay? And so this is what a mathematical series is, and so this sum continues. Now, you might say, well, if these quantities are all positive, right, it seems like when I add them all together, I get infinity, right? The sum is equal to infinity if all of these terms are positive. You'd be tempted to say that, okay? But for instance, right, look here, right? So look at this thing. So this sum that Leibniz computed, all of the terms are positive, right? We even worked out a few of these when we did it. So the first term, if I don't do this breaking apart thing, right? If I'm just looking at this, entirely ignore the fact that this is algebraically the same as this. So just looking at this thing, what are my terms in 2 over n times n plus 1? Well, let's just see. So the first term, when n is equal to 1, this is 2 over 1 times 1 plus 1. So that's 2 over 2. That's just 1, so that's positive. When n is equal to 2, this is 2 over 2 times 3. So that's 2/6 or 1/3, again positive, right? And that's, of course, true. When n is some positive number 1 or bigger, 2 over n times n plus 1 is always going to be positive. But it's decreasing, right? That's an important fact. It's positive, but it is decreasing, okay? It's getting smaller. We started at 1, then we go to 1/3, and then when n is equal to 3, this is 2 over 12, so this is 1/6, and so on, okay? And so Leibniz showed it wasn't entirely rigorous, but we know now that it's right. This is the correct sum. So this sum, if you sum up all these terms, you get 2. And there is a way to make that rigorous. The way to do that is to say, well, this is a series, okay? We can consider what is called the sequence of partial sums. So what is the sequence of partial sums for this series? It is a sequence defined from the series where the jth term in the sequence is just the sum up to j. Okay, and so if I have some sequence that runs from a sub 1 off, infinitely. So, of course, all these could be the same. None of these have to be increasing. Just because the indices are increasing doesn't mean all of these are increasing or anything. They could all be the exact same number. That would be a constant sequence, just a sequence that is the same number repeated infinitely many times. Okay, every single one of these could be 0. Every single one of these could be negative. They could alternate between 1 and -1. Okay, so you can literally, there's no restriction here. A sequence is simply a set of numbers, right, indexed like this. Okay, and so what's the sequence of partial sums? So the sequence of partial sums is defined, S sub j, a single term, is defined as the sum from n equals 1 up to j of a sub n. So this is literally just a sub 1 plus a sub 2 plus a sub 3, and I sum all of them up, but I stop at the jth term. I stop here. So every S sub j is just a finite sum. Okay, I joke with my Calc 2 students when I teach Calc 2, when we get to sequences of series, typically Calc 2 students consider sequences of series to be by far the hardest part of Calc 2, but I joke with them and tell them that actually it's just adding, right? We're just adding stuff. So literally this is just a finite sum, right? I'm just adding j numbers together, right? Okay, so this is my sequence of partial sums. Now, for a sequence, we can talk about the discussion of a limit. Now, Leibniz, Newton, and Euler understood the conceptual idea behind the limit of a sequence. Okay, but they didn't quite have the terminology down 100%. As I've said many, many times, that wouldn't be solved until the late 1800s. Okay, and so they didn't quite have the terminology down, but now we have the benefit of being able to rigorously define the notion of the limit as n goes to infinity of a sequence. So say S sub n, okay? Or since we're using n as our dummy variable, maybe I'll rewrite this as j, right? So the limit as j goes to infinity of S sub j. Now the thing about a limit of a sequence is it either exists or it doesn't. Okay. Now, it could just flat out not exist. Imagine a sequence that was just an infinite alternation of 1 and -1, right? So your sequence starts at 1, the next entry in the sequence is -1, the next entry is 1, and then back to -1, and it does that forever. That's what it always does. The limit of that sequence as j goes to infinity is nothing. It doesn't exist. It has no limit. Okay, so maybe this limit doesn't exist. For some sequences, it's really easy to see what the limit is, just conceptually. Let's start out with the sequence that is defined as a sub n is the sequence 1 over n. Okay, as n goes from 1 to infinity. So what does this sequence look like if I write it out as a set? It's 1, then it's 1/2, then 1/3, then 1/4, then 1/5, and so on. Right? And if I want to discuss the limit as n goes to infinity of that sequence, I'm not going to go through the rigorous definition here, but what is that limit? What is this sequence approaching? Well, 0. It's approaching 0. And the reason it's approaching 0 is if I go out to the 100th term, where am I? I'm at 1 over 100. If I go out to the 10 millionth term, I'm at 1 over 10 million, right? You can see that I'm getting very close to 0. In fact, I'm getting arbitrarily close to 0, right? If we rephrase this as Zeno's paradox, right, I am getting as close to 0 as you want. I'm never touching it, right? So just like in Zeno's paradox, right, I'm never touching it, but I'm getting as close to it as you like, okay? And what we say is that there's not a single term in this sequence that is equal to 0. No matter how far out you go in the sequence, there's not a single term that is identically equal to 0. But because we can get as close to 0 as we like, if we just keep going out in the sequence, we say that its limit is 0. So 0 is not one of these numbers, but these numbers are getting closer and closer, arbitrarily so, to 0. Okay, and so then we say the limit of this sequence is 0. So going back to our sequence of partial sums, a limit exists or it doesn't exist. Let's say that it exists and it is equal to s. Okay, now the example I gave of non-existence of a limit before with minus 1, 1, minus 1, 1, minus 1, that's one way of not existing. But there's another instance of a limit technically existing in the sense that the sequence goes to something, but it's not finite, right? So let's revisit my example here. So let's pick the sequence a sub n, which is just n, as n goes from 1 to infinity. So what is this sequence? This is the sequence that's 1, 2, 3, 4, 5, 6, and so on. Now, what is the limit as n goes to infinity of a sub n? Now, it doesn't exist as a finite number, right? There's no number I can identify that this thing is approaching, but we say that this sequence has limit infinity. Okay? Its limit is infinite, right? What this means is that what we're really saying here is we're not really thinking of infinity as a number, right? We're saying that this sequence gets arbitrarily large. Arbitrarily large? Yeah, that's right. So when you see this written out, what's really being said here is that this sequence gets arbitrarily large. It's not that we're thinking of infinity as a number. Just saying the sequence gets as large as you like. Okay? All right. But it turns out that if this limit exists and it is finite, we say that the sum of the series is this S, whatever it is. Okay, so whatever this limit of the sequence of partial sums is, that is what we call the sum of the series. So revisiting this problem with Leibniz, okay, maybe I'll do it on another piece of paper. So revisiting Leibniz's problem and doing it in a way that's 100% legit. I think I did this actually when I first mentioned the problem. So the sum from n equals 1 to infinity of 2 over n times n plus 1. So if I look at the sequence of partial sums, so to see what that is, I use Leibniz's trick and I rewrite that fraction as a partial fraction. So that partial fraction is 2 times 1 over n minus 1 over n plus 1. And you can just check that algebraically that all works out. So now that we've rewritten it like this, let's look at the sequence of partial sums. So what is like S sub 2, right? So S sub 1 is, well, let's just start at the beginning, right? So if we're looking at the sequence of partial sums, S sub 1 is equal to 2 times 1 over 1 minus 1 over 1 plus 1, right? So this is 2 times 1 minus 1 half. Okay. All right. What is S sub 2? So this is 2 times 1 over 1 minus 1 over 1 plus 1 plus 1 over 2 minus 1 over 2 plus 1. All right, so rewriting this, this is 2 times 1 minus 1 half plus 1 half minus 1/3. And so these cancel, and I have 2 times 1 minus 1/3. Okay. And so let's do one more so that you really see what's going on here. So S sub 3, this is 2 times 1 over 1 minus 1 over 1 plus 1 plus 1 over 2 plus, 1 over 2 minus 1 over 2 plus 1 plus 1 over 3 minus 1 over 3 plus 1. And so what is this? This is 2 times 1. The minus 1/2 and 1/2 cancel. The minus 1/3 and 1/3 cancel. And I'm left with 1 minus 1/4. And so what is the pattern here? So the pattern, if you compute the j'th entry in the sequence of partial sums, this turns out to be 2 times 1 minus 1 over j plus 1. And then I take the limit as j goes to infinity of this sequence of partial sums. That is the limit as j goes to infinity of 2 times 1 minus 1 over j plus 1. So look at this quantity. The only thing that depends on j is this fraction here. If j is going to infinity, 1 over j plus 1 goes to 0 as a limit, right? As j is getting huge, 1 over j plus 1 is getting very, very small. And so this is 2 times 1 minus 0, basically. So this is 2 times 1, which is 2. And this is the rigorous way of doing it. And so Leibniz was right. This is equal to 2. Okay. And so this is one of your examples of how to sum one of these series. Okay. And it turns out you can do this for every telescoping series. Okay, so going back, every telescoping series can be summed. So every telescoping series can be summed in this way. Okay, the computation that I did in my PhD thesis involved not a telescoping series, but another type of series, which is the only other general type of series that we know how to sum. Okay, so what is an example of that? Well, this is actually something that was known even to Archimedes. So there are geometric series. So what is a geometric series? So a geometric series is a sum from, say, n equals 0 or 1, some starting place, to infinity, of a number r, okay, to the n, where r is a positive number that's less than 1. Okay. If you write out this series, right, this sum from n equals 0 to infinity of, say, r to the n, this is 1 plus r squared plus r cubed plus r to the 4th plus r to the 5th, and so on. This is a geometric series. Okay. Now, how do you sum a geometric series? So a geometric series is something that Archimedes actually summed in order to compute some of these areas. And the reason it's called a geometric series is because of how it arises and as exactly the terms in these area computations, right? So this method of exhaustion that the ancient Greeks used and that Archimedes kind of perfected in his works, this what was required eventually was summing a geometric series. Okay, and so what is this? What is the method for actually doing this? So let's say, for instance, that let's say that I consider this as some kind of like infinite polynomial, right? What happens if I take this thing, so forget about this for a second. What happens if I take this thing and I multiply this entire thing by 1 minus r. What do I get? So forget about this for a second. We're going to block this out entirely. Okay. So this is what we have. We're multiplying this entire thing by 1 minus r. What do I get? Well, I get a copy of this thing because that's multiplying by 1. So I have 1 plus r squared plus r cubed plus r to the 4th plus r to the 5th and so on. Infinitely many terms, right? And then I have minus r times that. Well, let's just go down the line. Minus r times 1 is minus r. Minus r times r is minus r squared. Minus r times r squared is minus r cubed. Minus r times r to the 4th is minus r to the 4th, and so on. Minus r to the 5th, minus r to the 6th, and so on. And so I get cancellation here. Everything cancels except this 1. So this is equal to 1. So if I take my geometric series that I've summed like this and I multiply by 1 minus r, what do I get? Well, I get 1. Well, what if I divide now both sides by 1 minus r? Means the sum from n equals 0 to r to the n is equal to 1 over 1 minus r. Right? Okay. So let's check this out to see if this gives us a reasonable thing if we apply this to some particular geometric series. Let's look at the sum from n equals 0 to infinity of 1/2 to the n, right? So this is only going to work when you pick an r that is between 0 and 1. So if we have 1/2 to the n here, what is this? So this is 1 plus 1/2 plus 1 over 2 squared, so that's 1/4, plus 1 over 2 cubed, which is 1/8, plus 1 over 2 to the 4th, which is 1/16, and so on. Okay, what is that according to this formula? According to this formula, that is 1 over 1 minus 1/2. Well, 1 minus 1/2 is 1/2, so this is 1 over 1/2, and 1 over 1/2 is 2. So question, does that make sense to you? That 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32 plus 1 over 64, if I keep going like that, that I get 2? Just try it. All right? Take out a calculator or plug in your computer as many terms of that as you feel, not lazy enough to plug in. So type in as many of those as you like and see how close you are to 2. When you type in more, are you getting closer to 2? Did you pass it up? So you're not going to pass it up. It's approaching 2. The more and more terms in that series, that sum you compute, you're going to get closer and closer to 2. Okay, if you use a computer to do like 10,000 terms in that sum, you are going to get something very, very close to 2. Okay, and so telescoping series and geometric series are basically the only two types of series that we can sum generally. So we can do this for every geometric series, we can do this for every telescoping series, we can compute a sum like this. It turns out these series are mega complicated, okay, to sum. Even though you're just adding, right, this is complicated. So here's an example of a series that you can't sum because it's divergent. Okay, so there's what's called the harmonic series. So the harmonic series is the sum from n equals 1 to infinity of 1 over n. So write out a few terms of that. This is 1 plus 1/2 plus 1/3 plus 1 over 4 plus 1 over 5 and so on. Okay. It turns out that this is infinite. So if you plug 10 terms into calculator, you're going to get some number. If you plug 100 terms in, you're going to get a larger number. If You plug 1,000 terms in, you're going to get a larger number, and it's not going to be clearly approaching anything. And the reason why is because it is diverging. Okay, this is a divergent series. So a divergent series is one that does not converge. Converge means the sequence of partial sums has a limit, and that limit's finite, and that means it has a sum. Now, in Calc 2, for the most part, students are concerned with saying whether or not a given series converges. Okay, there are a number of tests that students are introduced to that help with that, but usually the answer to a question is it converges or it diverges, right? That's your answer. Finding the thing that it converges to, computing the actual sum, is extremely hard. In fact, I will convince you immediately here in just a few minutes of how hard this is, in that there is a sum that is very related to the two sums I'm about to write now. And if you could sum it, if you could actually find what that is equal to, it would instantly make you a very famous mathematician. So, what is the Basal problem? So the Basal problem wants to sum something that kind of looks like that, right? So the Basal problem, it asks, what is the sum from n equals 1 to infinity of, instead of 1 over n, it's 1 over n squared. Now there's a number of methods to show that this thing does converge. So in Calc 2, this is done in a number of ways. So there's the p-test is one example of using this, or of showing that this thing converges. But actually showing what it converges to was the question. So it was known that this converged to something. It just wasn't known what. Okay, and so Euler solved this. If we write out what this thing is, let's write out the first few terms. So this is 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared plus 1 over 6 squared, and so on, right? So exactly what I wrote later. So earlier, 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 plus 1/36, and so on. What is that? Euler found that this is pi squared over 6. Now, I will go over a proof of this in maybe a week or so, just because I think it's awesome to see it. And based on the earlier power series and Taylor series stuff that I talked about, I'll actually be able to do it in a pretty presentable or accessible way. The method that he used to do this is totally ingenious. It's actually amazing that he came up with this. And while it was known that this thing converged, no one had any clue that this is what it converged to. So no one thought that this converged to pi squared over 6. Now it turns out that using methods very similar to how Euler did this, you can actually sum this thing too. In fact, the even powers of n in this denominator here, you can sum. I believe this is pi to the 4th over 90. I think. I may have to correct that. That's just off the top of my head. I think that's what that is. And this uses a very similar method to what Euler did. So you can actually take care of the even powers of n here, right? But let's just do the next thing. All right, so this is the sum from n equals 1 to infinity of 1 over n cubed. What is this? No one knows. This has never been computed. Okay, it has been a quantity of interest for hundreds of years, but it has never been computed. And I'm not sure really any progress has been made on this in the last several in the last several years, in several decades, I think. I'm actually not entirely sure. I'd have to look up the progress, and I can do that when we're going over analysis stuff. This starts to intersect multiple areas of math, though. You might say, why would something like this be hard? And of course, this is the simplest one that is hard. 1 over n to the fifth also isn't known. The sum of the series involving 1 over n to the seventh also isn't known. So none of those odd ones are known, and this one is unknown. So what is this related to? This is related to something called the Riemann zeta function. And this is why it's so hard. Okay, so I'm not going to define the Riemann zeta function here. I'll define the Riemann zeta function here. So here's zeta of s is the sum from n equals 1 to infinity of 1 over n to the s, where s here is a complex number, so don't worry about that little tidbit. But this zeta of s is exactly this thing. This is an extremely complicated function. It's so complicated, in fact, that a very simple property of it, which is where its non-trivial zeros lie. So this thing has zeros, like a polynomial does, right? It has places where it's equal to 0. And where those zeros lie is the topic of interest in a statement called the Riemann hypothesis, or the Riemann zeta hypothesis. So if you've never heard of that, you can look it up, and I might talk about it a little later. But this is probably the most famous open question in all of math, and I can't possibly get into all of the implications it would have for a variety of fields, and likely the proof of it, would probably introduce some pretty awesome math that could be used in a lot of other ways too. So whatever this is just zeta of 3. Right? So zeta of 3 is that quantity. Right? So whatever this number is just the value zeta of 3. This is one of the Millennium Problems, Dan. Yes, this is one of them. So this is it was posed in the mid-1800s by Bernard Riemann, who we will talk about. Regardless of what direction we go in, we will talk about him because very important in analysis and very important in geometry as well. So, anyway. So that is one quick way of me kind of explaining, like if you had a question like why would it be so hard to compute something like this, it's because it's tied in with the Riemann zeta function. And so, but another way to look at this is that the zeta function of 2 is pi squared over 6. Right? And Euler computed that. The main thing that makes this so important is Euler was the first person to sum a series like this that was not telescoping or geometric. So that's it. And if you are summing a series that is not telescoping or geometric, the likelihood of you being able to do it is almost 0. Okay, it's just so hard to deal with these things. Okay, another example of Euler contribution. So Euler discussed what are called the 7 bridges of Königsberg problem. So this is the bridges of Königsberg. So Königsberg at the time was a city in Prussia. That's an E, that's right. But it's now a city in Russia. But it was famous for its configuration of bridges. So this is the bridges of Königsberg problem. And here is the problem. Okay, you have land masses in Königsberg, or at least in the time that Euler discuss this problem. So you have a landmass here. You have a landmass in the middle of a river. Okay, you have another landmass here, and you have one more landmass over here. Now, the 7 bridges of Königsberg were arranged in the following way. So here is one of them. Maybe I'll draw it as an actual bridge. Here's another. Okay, here's another. Here's 2 more. And we have 2 more like this. Okay. All right, so this was actually how the city was configured. Okay, I mean I drew a crude picture, obviously, but this is actually how the bridges of Königsberg were arranged. Okay, so then what was the problem? So the problem, the question: how can I plan a walk through the city that traverses each bridge only once? Okay. So once and only once. Okay. I have to try to plan a walk through the city. Okay. Now, right, you're going to immediately start thinking, well, there's some options here, right? Maybe you start your walk over here. And if you start your walk over here, you start trying some ways of doing this, and you quickly see, oh, okay, I don't really see how to make this happen, right? So maybe I start here, and it's like, okay, I cross this bridge, this one, then I cross back through these 2, cross here. When I cross back, I'm going to cross a bridge. If I want to get off this island, I'm going to cross a bridge I already crossed, so I can't do that. But then if I cross over here, now I can't get back to cross this last remaining bridge. And you are going to quickly see that regardless of where you start, you're going to run into this problem. Okay, now you might look at that and say, well, one, like, who cares? What's the big deal, right? But it quickly becomes an interesting issue, because how do you deal with this mathematically, right? You should be able to, you should be able to break this down in such a way that this just becomes strictly some math problem, right? Whether it's in geometry or it's in something, right? What tools do you even use to devise a solution to this? So that's the most important thing to come of this. So the answer, and this was due to Euler, was that you can't. It's impossible. Okay, and he was able to prove that it is impossible. Okay, so he was able to prove mathematically that it is impossible to do this. Okay, and in working on this problem, he was developing the very basics of a couple of things, a couple of different areas of math. So in working on this problem, Euler had discovered the early fundamentals of graph theory and topology. Okay. I'll say a little bit more about these two later when we're kind of in the special topic stuff. Topology is often called it's the mathematics of continuity, but that can kind of hide to someone who doesn't maybe think about continuity exactly on like 100% rigorous terms. It's not that helpful necessarily. It is a way of thinking about the mathematics of doing geometry where you're allowed to bend things. You're allowed to bend things, and you can bend things in some pretty lenient ways, but you can't break them. So you can bend but not break. It's geometry where you can bend but you can't break. Okay, breaking is a discontinuous thing, so I want to only do these continuous operations of blobbing things about, okay, morphing them around in a way that doesn't break anything. Graph theory itself is the study of graphs. That's maybe not that helpful. But the idea is that there's a way to define the mathematical notion of a graph. It consists of nodes, okay, so which are these points, and edges, right, which connect these vertices, right, in a certain way. So maybe this is the graph that you have, okay, on these nodes. And you quickly see how a study of connectivity problems of graphs is intimately related to this when you take this picture and you get rid of all of the stuff that doesn't really matter and what is actually important about this picture. So when you reduce it in a proper way, you can turn this picture into a graph. Okay, and so this is really asking a question that concerns connectivity of graphs and being able to reach certain nodes from other nodes, traversing these edges some number of times. Okay. And so why this is important is that math had no way of dealing with problems like this, right? Euler was kind of the first to figure out how to deal with questions like this because there just weren't any mathematical tools to even understand what was going on here. Okay. But it wasn't all of the innovation in fields that did not exist, say, at the time of Archimedes. Euler was also very good at contributing to fields that have been studied for thousands of years. So Euler also discovered what's called the Euler line. What is the Euler line of a triangle? So I am going to construct a triangle here. I'm going to try to make one that's not, too nasty, but also not too atypical. I just didn't want it to be isosceles. So there we go. There's triangle. Okay, so what is the Euler line? So the Euler line is the fact that the circumcenter, I'll remind you what these quantities are. So the circumcenter, the orthocenter, and the centroid or center of mass of a triangle are collinear, i.e. they lie on the same line. This line is now called the Euler line. So we have the circumcenter, the orthocenter, and the centroid. What is the circumcenter? Okay, so the circumcenter is the meeting point of the right bisector. So since we're going to need bisectors anyway, let's kind of eyeball the midpoints here. That looks like a midpoint for that segment, right? And maybe here's the midpoint for this segment. Does that look right? Almost. And here's the midpoint of this segment, right? Now, for a nasty triangle, some of these lines that I'm going to be drawing and some of these points that I'm going to be drawing might lie outside the triangle. So whether they're inside or outside the triangle, depending on how weird your triangle is, that's these things are not. Some of these quantities are not always going to be in the center, or they're not always going to be inside the triangle. Like I said, depending on how flexible you are with these various types of centers. And it turns out it's not just these three, but these are the three that Euler originally proved were collinear. So the circumcenter is the intersection point for the right bisectors. So at each of these, maybe I'll use a different color here. So at each of these midpoints, I'm going to draw in the right bisector here. So there. And here is this one. And here is this one. And of course, you'll notice that when I go to draw this third one, hey, it actually meets those other two. That's a fact from geometry that had been known since the days of Archimedes. So what about in fact, even before Archimedes, this was known to Euclid. The orthocenter is the intersection of the altitudes, right? So what are my altitudes? My altitudes are dropping perpendicular from opposite vertex to the opposite side. So if I start at this vertex, my altitude is the perpendicular drop to the opposite side. So there it is. Okay, if I start at this vertex, perpendicular to the other side is actually very close. This thing itself. Okay, there it is. And then if I start at my last vertex, perpendicular to other side, hey, there it is, right? So here is my orthocenter, right, black. The circumcenter I will make as red. Okay, and my centroid is just the concurrence of the medians. The medians here are just the connection of opposite vertex to midpoint. So I'll maybe draw that in blue again. Okay, and so what are those? So here, let me draw in. There's one median. Here's another. And here's one more. You'll see that those intersect at this point here. That is my centroid. Okay. So then what is the Euler line? I'll draw it as a red line here. It is the line, those three are collinear along. So this is my Euler line. So this is something that escaped the ancient Greeks, and it took Euler to figure out how to show that these three things were collinear. In fact, there's other notions of centers of triangles that can be computed, and almost all of them also lie on the Euler line, though not necessarily inside the triangle, depending on how weird your triangle is. Okay. So you might say, like, how did Euler do this? This is a problem that doing it in Greek-style geometry would be kind of annoying. It would be kind of a really nasty problem. Well, maybe if I thought about it a little bit more, maybe there's a slicker way of doing it that way. But off the top of my head, in Greek-style geometry, this is kind of a nasty problem. But it's not that bad at all using linear algebra. So using linear algebra and the notion of vectors, some of these arguments involving triangles become really, really easy, and that's how Euler did this. So we're still not at the end of Euler's contributions. I'm going to say like two more things and then move on, and then I'll finish out with a couple other mathematicians, Lagrange and Laplace, that won't take very long, and then we'll be on to the new material that I'm gonna, that I'm coming up with based on your poll. So anyway, that's the plan. I posted homework 3 today. It's due sometime next week. Next week, after homework 3 is due, I'll post your last homework, which is just kind of a roundup of some of these last mathematicians we talked about. And then your final exam will be, I can't remember what day it's scheduled for. I'll have to look again, but it'll be similar format to the midterm, and you'll have at least like 5 days to do it. So anyway, that's the plan. So anyway, I guess I'll see you all on Friday.